On July 1st, 2025, astronomers in Chile discovered something that would change everything we thought we knew about comets. Something that came from so far away it predates our own sun. Something that behaves in ways that make scientists question the very laws of physics we've built our understanding of the universe on. Its name is 3I divided by Atlas, and the more data we collect, the less sense it makes. This isn't just another space rock passing through our neighborhood. This is the third confirmed interstellar visitor ever detected, and it's bringing with it mysteries that are keeping some of the world's top astrophysicists awake at night. Because when you look at the data, when you really dig into what this thing is doing, you start to realize something disturbing. Everything about 3I divided by Atlas is wrong. It's too old. It's too big. It's moving water in places where water shouldn't move. Its chemistry doesn't match anything we've ever seen in nature. It has jets pointing in the wrong direction, and its trajectory through our solar system has astronomers calculating probabilities that make winning the lottery look like a sure bet. Some are calling it a time capsule from the early universe. Others are calling it the most important scientific discovery of the decade. And a few, including one very famous Harvard astrophysicist, are asking a question that sounds like science fiction but is backed by actual data. Could this be something other than natural? Now, before you roll your eyes, I need you to understand something. The scientists studying this object aren't conspiracy theorists. They're not chasing clicks or trying to sell books. They're looking at hard evidence that doesn't fit any model we have. And they're doing what good scientists do when the data contradicts their expectations. They're asking uncomfortable questions. Over the next hour, we're going to walk through every single anomaly surrounding 3I divided by Atlas. We're going to look at the chemistry that should be impossible. We're going to examine the water activity that breaks the rules. We're going to calculate the odds of its trajectory. And we're going to explore why some researchers are taking seriously the possibility that this might not be entirely natural. But here's what makes this story even more incredible. Right now, as you're watching this, 3I divided by Atlas is making close passes by Mars and Jupiter. Multiple spacecraft are racing to get a better look at it. And within the next few months, we might get data that either explains everything or deepens the mystery even further. The clock is ticking. The observations are happening. And what we discover could rewrite not just our understanding of comets, but of how matter, chemistry, and maybe even life itself travels between the stars. So let me take you through this from the beginning, because the story of 3I divided by Atlas starts in a place so ancient, so far away, that it challenges everything we think we know about our cosmic neighborhood. The discovery. When the Atlas Survey Telescope in Chile first picked up this object, astronomers thought they knew what they were looking at. Another comet. Maybe an interesting one, sure, but just another ball of ice and rock doing its thing in space. They were so wrong. Within days of the initial detection, something became clear. This wasn't from our solar system. The trajectory was all wrong. The speed was all wrong. This thing came from somewhere else. Somewhere out there in the vast darkness between stars. And that alone would have made it special. We've only confirmed 3 interstellar objects ever. The first was Oumuamua back in 2017. That strange cigar-shaped thing that sparked 1,000 debates. The second was Borisov in 2019, which looked more like a normal comet. Something familiar. Something that made sense. But 3I divided by Atlas? It's in a category all its own. Let me put this in perspective for you. Oumuamua was maybe 400 meters across. Small. Borisov was even smaller. Just a few hundred meters. These were cosmic pebbles, really barely big enough to see. 3 divided by Atlas is estimated to be up to 20 kilometers across. 20 kilometers. That's not a pebble, that's a mountain. That's bigger than some of the asteroids that could cause mass extinction events here on Earth. This thing is massive in comparison to the other interstellar visitors we've detected, and that size difference isn't just impressive. It tells us something profound about where this thing came from and how long it's been traveling. Because when you're that big, you don't erode away quickly. You don't lose your mass easily to the harsh radiation of interstellar space. You can survive for a very, very long time. How long are we talking about? Try 10 billion years. Yeah, you heard that right. The estimates based on its trajectory and composition suggest that 3 divided by Atlas formed around 10 billion years ago. That's more than twice the age of our Sunday. That's older than Earth by 6.5 billion years. This thing is ancient in a way that's hard to wrap your head around. When 3 divided by Atlas first coalesced in some distant stellar nursery, the universe was less than a quarter of its current age. The Milky Way was still figuring out what shape it wanted to be. The solar system where you and I exist right now didn't even have the raw materials yet to begin forming. And this comet was already out there, drifting through space. Scientists believe it originated from a region of the Milky Way called the Thick Disk, which is populated by some of the oldest stars in our galaxy. This is the ancient borderland where the early chemistry of the universe was still playing out. And somehow this object formed there, got ejected, and has been wandering the galaxy ever since. Think about that journey for a moment. 10 billion years of drifting through the cold, empty void, surviving radiation that would destroy most materials, dodging gravitational fields that could have torn it apart, witnessing the birth and death of countless stars. And now, by sheer cosmic chance, its path has intersected with ours. When astronomers realized they were looking at something this old, the excitement was immediate. Because if you're an astrochemist or a planetary scientist, 3 divided by Atlas represents something almost too good to be true. It's a sample of the early galaxy, a frozen time capsule containing chemistry from an era we can barely study otherwise. The materials locked inside this comet might tell us what the universe was like billions of years before Earth even existed. It could teach us about the conditions that led to the formation of planets like ours. It could show us what building blocks were available when the first potentially habitable worlds were taking shape. This isn't just interesting. This is scientifically priceless. But here's where things start to get weird. Because as astronomers began gathering more data, they realized that 3 divided by Atlas wasn't just old and big. It was doing things that comets aren't supposed to do. The water problem? Let me explain something about how comets normally work, because understanding what's normal makes it much easier to appreciate just how strange 3 divided by Atlas really is. Comets are basically dirty snowballs. They're made of ice, rock, dust, and frozen gases all clumped together. And for most of their existence, they're just cold, inert objects floating through space. Nothing exciting, just frozen balls of material. But when they get close to a star, something changes. The heat from the star starts warming up the surface of the comet. And when that ice heats up enough, it doesn't melt. It sublimates. It goes directly from solid to gas, skipping the liquid phase entirely. That's what creates the spectacular tails we associate with comets. That's what makes them visible and beautiful. The sublimating ice and dust streaming away from the nucleus, pushed by solar wind and radiation pressure, creating those gorgeous flowing tails that can stretch for millions of kilometers. But here's the key detail. This process only happens when the comet gets relatively close to the Sunday. There's a rough boundary in our solar system, somewhere around the orbit of Jupiter, where things start getting warm enough for water ice to sublimate at a meaningful rate. Beyond that distance, comets are dormant. They're just frozen rocks. Nothing's happening. They're waiting for the day they might get close enough to a star to wake up. That's the rule. That's how it's supposed to work. 3i divided by Atlas is breaking that rule in a spectacular way. When Swift and Hubble turned their instruments toward this comet, what they saw made them do a double take. They detected water vapor, lots of it. This thing was actively expelling water into space at a rate of about 40 kilograms per second. Now, 40 kilograms per second might not sound like much compared to the size of the comet, but think about it this way. That's like having a fire hose running at full blast continuously, spraying water into the vacuum of space. And here's the problem. When these observations were made, 3i divided by Atlas was still nearly 3 times farther from the Sun than Earth is. Let me make this clear. At that distance, at that temperature, this water activity shouldn't be happening. Not at this scale. Not with this intensity. The solar radiation simply isn't strong enough to provide the energy needed to sublimate ice at this rate. Regular comets at that distance are essentially dormant. They might have some very minor activity, sure, but nothing like what 3i divided by Atlas is doing. This is like finding someone running a marathon in Antarctica, wearing a t-shirt and acting like it's a warm summer day. Something else is providing energy to this comet. When scientists analyzed the spectroscopic data more closely, they found something even stranger. The water wasn't just coming from the surface. The signature suggested that ice grains were being ejected from the comet and then sublimating in space, away from the nucleus. This is bizarre. This hints at some kind of internal activity. Something inside the comet is energetic enough to launch material into space, and then that material is sublimating once it's free. What could cause that? Some researchers have suggested that maybe there are pockets of volatile materials deep inside the comet that are warming up and creating internal pressure. Maybe there are radioactive materials decaying and generating heat. Maybe the structure of the comet is so unusual, so porous, that solar radiation can penetrate much deeper than normal. But none of these explanations fully account for what we're seeing. The scale of the activity is just too high. The distance is too great. Something doesn't add up. And here's another detail that makes this even weirder. Studies of the comet's surface suggest that only about 8% of it is actively sublimating ice. 8%. For comparison, a typical solar system comet during peak activity might have up to 35% of its surface releasing material. So 3i divided by Atlas has less active surface area than a normal comet, but it's somehow producing way more water activity than it should at that distance. How is that possible? The implications of this are profound, because if this comet has some internal heat source, some mechanism we don't understand, then it's not just a frozen relic. It's an active, dynamic object with processes happening inside it that we've never seen before. And that internal activity? That's where things start getting really interesting. Because when you have unexplained internal energy in an object from another star system, scientists start asking questions that sound almost impossible. But before we go down that road, we need to talk about the chemistry. Because the chemical composition of 3i divided by Atlas is possibly the single most baffling piece of this entire puzzle. The nickel anomaly. Chemistry is like a fingerprint. When you analyze the light coming from a comet, you can see absorption lines and emission lines that tell you exactly what elements are present. It's one of the most reliable tools we have in astronomy. You point a spectrograph at something, you look at the light, and boom, you know what it's made of. When astronomers pointed their instruments at 3I divided by Atlas and looked at its coma, that glowing cloud of gas and dust surrounding the nucleus, they found something that shouldn't exist: nickel vapor. Now, finding metals in comets isn't unheard of. Comets contain trace amounts of various elements, including metals. But here's the thing about nickel. In nature, in every comet we've ever studied, in every asteroid, in every planetary sample, nickel and iron go together. Always. These two elements are formed together in the hearts of dying stars. They're ejected together in supernova explosions. They condense together in stellar nurseries. When you find one, you find the other. They're cosmic siblings, born together, traveling together, existing together. It's one of the most fundamental patterns in cosmic chemistry. Iron and nickel are a package deal. 3I divided by Atlas has nickel. Strong nickel emission lines in its spectrum, clear as day, no ambiguity. But iron? Almost nothing. The signature is so weak it's barely there. This is not normal. This is not how nature works. In all of our studies of solar system objects, of meteorites, of planetary cores, of stellar spectra, we have never seen nickel and iron separated like this. Never. Let me tell you what this means in practical terms. If you want to separate nickel from iron, you need to do chemistry. Deliberate, intentional chemistry. On Earth, we do this in industrial refineries. We heat metal ores to specific temperatures. We use chemical processes to extract one metal from another. We employ techniques that require planning and understanding and equipment. Nature doesn't do this. Cosmic processes don't preferentially create nickel without iron. There's no known natural mechanism that would produce this separation on the scale we're seeing. So, how is it happening? The leading hypothesis is that there are unusual organometallic compounds in the comet, specifically something called nickel tetracarbonyl. This is a molecule where nickel is bonded to carbon monoxide groups, and it has a very special property. It releases nickel vapor at much lower temperatures than iron compounds do. If the comet has significant amounts of nickel tetracarbonyl, then as it warms up, the nickel gets released first, while the iron remains locked up in compounds that need more heat to break apart. Okay, fine. That could explain the observations. But here's the next question. How did nickel tetracarbonyl get there in the first place? These organometallic molecules don't form easily in space. They require very specific conditions. Ultra-cold environments with the right mix of elements and the right chemical pathways. And even then, it's not clear how you'd get enough of this stuff to produce the signal we're seeing. Some researchers have suggested that 3I divided by Atlas formed in an environment fundamentally different from anything in our solar system. Maybe the chemistry in that ancient region of the Milky Way allowed for molecular formations we don't see locally. Maybe the early universe had chemical pathways that are rare or impossible now. That's possible. But it's also speculative. We don't have strong evidence that such exotic chemistry was common 10 billion years ago. And this is where things get uncomfortable for some scientists, because there's another possibility, one that most researchers don't want to talk about publicly, but that's mentioned in quiet conversations and carefully worded papers. What if the nickel-iron separation is artificial? What if something processed this material? Now I can already hear the objections, and they're valid. Just because something looks unusual doesn't mean it's artificial. Nature is capable of incredible diversity. We discover weird chemistry all the time. The universe is strange, and we're still learning. All of that is true. But here's what's also true. The nickel-ion separation we see in 3I divided by Atlas is identical to the signature you'd see in refined industrial metals. On Earth, when we separate these elements for manufacturing purposes, we get exactly this pattern. And that similarity is hard to ignore. I'm not saying this is proof of anything. I'm not claiming we found alien technology. What I'm saying is that we have a chemical anomaly that doesn't fit our models of natural processes, and that anomaly happens to match industrial signatures we create intentionally. That's worth noting. That's worth studying. That's worth taking seriously, even if the explanation ultimately turns out to be some exotic natural process we haven't discovered yet. But the nickel problem is just one piece of the puzzle, because 3I divided by Atlas has more anomalies, and each one, taken alone, might be explainable, might be within the realm of weird but natural. But when you start adding them together, when you look at the full picture, that's when scientists start getting nervous, because the next anomaly involves the comet's jets. And what they're doing is physically wrong. The backward jet. Comets have jets. We've known this for a long time. These are focused streams of gas and dust that shoot out from active regions on the nucleus. They're created when ice sublimates and the pressure of the expanding gas carries dust particles along with it. And these jets follow a very simple rule. They point away from the sunday. The reason is straightforward physics. The sun's radiation heats the surface, creating pressure that drives material outward. And the solar wind, that stream of charged particles flowing from the sun, pushes the gas and dust away. Everything gets blown in the anti-solar direction. This is why comet tails always point away from the sun, even when the comet is moving away from it. The tail isn't trailing behind like you might expect. It's always being pushed outward by solar forces. This is basic, well-understood, textbook comet physics. 3I divided by Atlas has a jet that points toward the sunday. I need you to understand how strange this is. Imagine you're standing in a hurricane-force wind. Everything around you is being blown backward. Trees bending, debris flying, everything moving in the same direction because the force is that strong. Now imagine one object defying all of that, moving forward into the wind. Not just resisting it, actually producing its own force strong enough to overcome the wind and travel in the opposite direction. That's what this antitail is doing. The solar wind at the distance where 3I divided by Atlas is operating exerts real pressure. It's not strong by Earth standards, but in the vacuum of space with these lightweight particles, it's significant. For material to move toward the sun instead of away from it, something inside the comet has to be producing thrust that overpowers solar radiation pressure and solar wind. That requires energy, a lot of energy. What could cause this? One possibility is that there are jets firing from the night side of the comet, the side facing away from the sunday. If those jets are strong enough, they could push the comet slightly, and the reaction force would propel material forward. But this explanation has problems. First, why would the night side be so active? There's no sunlight there to drive sublimation. And second, the observations show this antitail is persistent. It's not an occasional thing. It's ongoing. Another possibility is rotational effects. Maybe the comet's spin is somehow directing material forward. But again, that doesn't explain the energy source. You still need something powerful enough to overcome solar forces. Some scientists have suggested that maybe there's a pocket of super volatile material that got exposed. Something like carbon monoxide ice, which sublimates at much lower temperatures than water. If a deposit of this stuff was suddenly opened up, it could release a lot of gas very quickly, creating a jet that's energetic enough to do what we're seeing. That's plausible. but it's also convenient. It's the kind of explanation you come up with when you need to make the observations fit natural processes, even if there's no direct evidence for those specific conditions. The uncomfortable truth is that we don't have a fully satisfying natural explanation for the anti-tail. We have ideas, sure, hypotheses, but nothing that accounts for all the observations cleanly. And here's what makes this even more intriguing. The anti-tail isn't the only directional anomaly. The comet's overall activity pattern is weird too. Remember how I mentioned that only 8% of the surface is active? Well, that active region isn't uniformly distributed. It's localized, concentrated in specific areas, and the way the jets are oriented, the way the material is being expelled, it doesn't look random. It looks almost deliberate. Now, I need to be careful here. Pattern recognition is something human brains are exceptionally good at. Too good sometimes. We see faces in clouds. We see messages in random noise. Our brains are wired to find patterns even when they're not really there. So the fact that the jet pattern looks non-random might not mean anything. It could just be the specific geology of this particular comet, the random arrangement of volatile deposits that happened to form in this configuration 10 billion years ago. But it could also mean something else. And when you combine this with the nickel anomaly and the water activity and all the other weird things about this object, you start to see why some scientists are asking questions that sound like science fiction. Because we're not done yet. There are more anomalies. And the next one involves the comet's optical properties, its color, its light signature, and what that tells us about the dust and ice mixture on its surface. Borisov, that second interstellar visitor, was rich in carbon monoxide and had the organic signatures scientists expected. 3, I divided by Atlas, is different. It has water. Yes, lots of water. But it's low in many of the complex organics we associate with life chemistry. It's almost like it's been selectively depleted in certain compounds while retaining others. What could cause that? Maybe the formation environment. Maybe wherever this thing was born had different chemistry than we're used to. Maybe the star it formed around had a different composition, produced different radiation environments, and that led to different molecular abundances. That's possible. But here's another thought. What if the organics were processed somehow? What if something happened to this comet during its journey that altered its chemistry in ways we don't understand? Or, and this is where things get really speculative, what if the composition isn't random? What if there's a reason for this particular mix of molecules? I'm not saying there is. I'm just saying that when you have an object with chemistry that doesn't match natural expectations, with water activity that defies physics, with metal ratios that look industrial, with jets pointing the wrong way, and with optical properties that suggest both extreme age and pristine preservation, you start to run out of simple explanations. And we're still not done. Because the next anomaly isn't about chemistry or physics, it's about probability. And the numbers are genuinely disturbing, the impossible trajectory. Let's talk about orbits for a minute. When an object is traveling through interstellar space and happens to pass through our solar system, its trajectory is essentially random from our perspective. It could come from any direction, at any angle, moving at any speed within the range of what's physically possible for interstellar objects. The solar system itself isn't random though. The planets all orbit the sun in roughly the same plane. We call this the ecliptic plane, and it's basically the flat disk where all the major planetary action happens. The sun's equator aligns with it. Most asteroids stay close to it, and the planets all follow orbits that are inclined by just a few degrees from this reference plane. Now, if you're an interstellar visitor just passing through, the odds that your trajectory would align with the ecliptic are pretty small. Space is three-dimensional. You could come from above, below, from any angle in any direction. The ecliptic is just one arbitrary plane among infinite possible planes. 3, I divided by Atlas, is inclined to the ecliptic by only 5 degrees. 5 degrees. That's not just close. That's eerily close. It's like throwing a dart from across the room and hitting not just the dartboard, but the bullseye. The odds of a random interstellar object having a trajectory this well aligned with our solar system's plane are extremely low. But it gets weirder. 3, I divided by Atlas's path through the solar system isn't just aligned with the ecliptic. It's threading a needle through multiple planetary encounters. During its passage, it's making sequential close approaches to Venus, Mars, and Jupiter. Think about that for a second. The solar system is mostly empty space. Planets are tiny targets scattered across vast distances. The odds of a random trajectory just happening to pass close to one planet are small. The odds of passing close to 3 planets in sequence? Astronomers calculated it. The probability is less than 0.005%. That's 5 in 100,000. Those are not good odds. Those are, you should buy a lottery ticket because this never happens odds. And yet it's happening. Now, before anyone jumps to conclusions, let me be clear about something. Low probability events happen all the time. That's the nature of probability. If something has a 1 in a million chance, and you do a million trials, you expect it to happen once. The universe is big. Interstellar objects are presumably common, even if we've only detected a few. It's entirely possible that we just happen to be observing one of the rare cases where the alignment works out this way. That's the rational scientific explanation, and it's probably correct. But there's something else, something that makes this trajectory even more remarkable. And this is the detail that made even hardened skeptics pause and take notice. The direction 3 I divided by Atlas came from, when you trace its trajectory backward through space, points to a region of the sky within 9 degrees of the source location of the famous WOW signal. If you don't know what the WOW signal is, let me give you a quick summary. In 1977, a radio telescope at Ohio State University detected a powerful narrowband radio signal coming from space. It was so strong, so unusual, and so well matched to the frequencies scientists predicted an artificial signal might use that the astronomer reviewing the data wrote "Wow" on the printout. The signal lasted 72 seconds. It never repeated. And despite decades of follow-up observations, we've never detected anything like it again from that region of space. It's the most famous unexplained signal in the history of SETI, the search for extraterrestrial intelligence. And while most astronomers now think it was probably a natural phenomenon, maybe something involving a comet or a stellar event we don't fully understand, it remains an enigma, a mystery. The one signal that we can't fully explain. And 3 I divided by Atlas is coming from almost exactly that same direction. The odds of this alignment by chance are about 0.6%. Again, that's low. Not impossible, but low. Now, I want to be extremely careful here. Correlation does not imply causation. Just because 2 things are associated doesn't mean one caused the other or that they're related at all. The WOW signal was 48 years ago. Any object traveling at the speeds we measure for 3 I divided by Atlas would have been nowhere near that region of space in 1977. So this isn't suggesting the comet sent the signal. That doesn't make physical sense. But it does mean that both the signal and the comet originated from the same general region of the galaxy. And that region, when astronomers study it, doesn't have anything obviously special about it. No major star clusters, no unusual stellar populations, nothing that would make you say, of course, that's where interstellar comets and radio signals come from. It's just another patch of sky. Except that it's given us two of the most mysterious events in modern astronomy. Is that meaningful? Probably not. It's almost certainly a coincidence. The universe is full of coincidences. But when you add this to everything else about 3I divided by Atlas, when you combine it with all the other anomalies, it becomes part of a larger pattern that's harder to dismiss. Because at this point we have an object that's impossibly old, impossibly active, chemically anomalous, physically strange, and following a trajectory that seems to defy probability, while also pointing back to one of the most famous unexplained signals in SETI history. And that's when scientists start to do something they usually avoid. They start asking the question that feels almost forbidden in serious scientific discourse. What if this isn't entirely natural? The Loeb scale. Avi Loeb is a professor of astrophysics at Harvard. He's the former chair of the Astronomy department. He's published hundreds of papers in prestigious journals. He's advised doctoral students, served on scientific panels, and contributed to our understanding of everything from black holes to cosmology to exoplanets. He's also become somewhat controversial in recent years for his willingness to seriously consider the possibility that some astronomical objects might have artificial origins. When Oumuamua, that first interstellar visitor, came through our solar system in 2017, Loeb wrote a paper suggesting that its unusual characteristics, its acceleration that couldn't be fully explained by outgassing, its odd shape, might indicate it was an artificial object. A light sail, perhaps, or some kind of probe. The astronomical community largely dismissed this. Most scientists felt that while Oumuamua was strange, it didn't require invoking technology. Natural explanations, even if they had to stretch a bit, were sufficient. Loeb stood by his position. Not claiming certainty, but arguing that the possibility deserved serious consideration. When 3I divided by Atlas was discovered, Loeb paid attention. And as the data started coming in, as the anomalies piled up, he developed something he calls the Loeb scale. It's modeled after the Richter scale for earthquakes, or the Torino scale for asteroid impacts. A way to quantify how likely an object is to be artificial rather than natural. The scale goes from 0 to 5. 0 means definitely natural. 5 means definitely artificial. Most objects would score somewhere in the middle, with increasing scores indicating increasing oddity. Loeb assigned 3I divided by Atlas a score of 2. Level 2 on his scale is defined as strange enough to warrant further investigation, multiple anomalies that don't have easy natural explanations, but not conclusive. Let me be clear about what this means and what it doesn't mean. It does not mean Loeb is claiming 3I divided by Atlas is an alien spacecraft. It does not mean he has evidence of technology. It does not mean he's certain of anything. What it means is that this object has enough anomalous features that the question of artificial origins deserves to be taken seriously as a hypothesis. Not as the only hypothesis, not even necessarily as the leading hypothesis, but as something that shouldn't be dismissed out of hand. Loeb points to 7 specific features that contribute to his assessment. First, the enormous mass and size. 20 kilometers is not just big for an interstellar object. It's big for any comet. If this were a spacecraft, if this were something constructed rather than naturally formed, being large would actually make more sense. You'd want something big enough to survive a multi-billion-year journey through space. Second, the composition anomalies. The nickel without iron. The depletion of expected organics like cyanogen while having high CO2. the unusual ratios that don't match what we see in natural objects. Each of these individually might be explainable, but together they paint a picture of chemistry that seems selective, almost curated. Third, the orbital inclination and those sequential planetary encounters. The probability of this happening by chance is so low that it makes you wonder if the trajectory was chosen rather than random. If you were designing a mission to study multiple worlds in a single pass through a star system, this is exactly the kind of path you'd want. Fourth, the spectropolarimetric properties. That extreme negative polarization, the red coma, the optical signature that suggests both incredible age and pristine preservation. It's like the object has protective characteristics that prevented degradation over its journey. Fifth, the water activity far from the sunday. The fact that this thing has an internal energy source powerful enough to sublimate ice in regions where solar heating alone can't account for it. Energy implies either exotic natural processes we don't understand or deliberate systems we haven't detected yet. Sixth, the anti-tail. Jets pointing toward the Sunday directional thrust that overcomes solar pressure. If you wanted to make minor course corrections during a long interstellar voyage, if you wanted to adjust your trajectory as you approached your destination, low-level outgassing used as propulsion would be a smart way to do it, and it would look exactly like what we're seeing. Seventh, the directional coincidence with the WOW signal location. Loeb emphasizes this one less than the others because he knows how weak coincidence arguments are. But he points out that if you were looking for signs of technological civilizations, and if you had detected a strong radio signal from a particular direction in 1977, you might want to send a probe to investigate. And that probe, traveling at speeds consistent with what we measure for 3I divided by Atlas, would arrive in our solar system right about now. Again, Loeb is not claiming this is what happened. He's saying the coincidences are worth noting. The vast majority of astronomers disagree with Loeb's assessment, not because they think he's stupid or unscientific, but because invoking artificial origins for something requires extraordinary evidence. And while 3I divided by Atlas is certainly extraordinary, most researchers feel that stretching natural explanations, even if we have to invoke rare conditions or unusual chemistry, is still more reasonable than jumping to technology. That's a valid position. In fact, it's the position most scientists should have by default. Extraordinary claims require extraordinary evidence, and this comet is weird doesn't meet that bar. But here's what makes this situation different from most could it be aliens discussions. We're gonna get more data soon. Right now, as 3I divided by Atlas continues its trajectory through the inner solar system, multiple spacecraft are racing to observe it. The Mars Perseverance rover has already captured images. The Mars Reconnaissance Orbiter is tracking it. The Juno spacecraft at Jupiter is preparing to make observations during the comet's closest approach to that planet. These aren't purpose-built missions to study 3I divided by Atlas. They're existing spacecraft that happen to be in the right place at the right time. But they have instruments that can gather data we've never been able to collect on an interstellar object before. We're going to get spectra at different wavelengths. We're going to measure the magnetic field around it. We're going to observe how it interacts with the solar wind in real time. We're going to track its trajectory with extreme precision to see if there are any unexplained accelerations or course changes. And most importantly, we're going to watch what happens as it gets closer to the sun and then moves away again. If this is a natural comet, its behavior should follow predictable patterns. The water activity should increase as it approaches perihelion, the closest point to the sun, and then decrease as it moves away. The jets should respond to solar heating in ways we can model and predict. If something else is going on, If there's an internal energy source that isn't solar dependent, we'll see anomalies. We'll see activity patterns that don't correlate with solar distance. We'll see thrusts that can't be explained by outgassing alone. Within the next 6 months, we're going to know a lot more about what 3I divided by Atlas really is. And that data will either put the artificial hypothesis to rest completely, or it will make it impossible to ignore. That's what makes this moment so significant. We're not just speculating about possibilities. We're actively gathering data that will give us real answers. The panspermia connection. There's another reason scientists are so excited about 3I divided by Atlas. One that has nothing to do with aliens or artificial objects and everything to do with the origin of life itself. The theory of panspermia suggests that life, or at least the chemical building blocks necessary for life, might travel between star systems on comets and asteroids. That instead of life emerging independently on every habitable world, maybe the ingredients get distributed throughout the galaxy by these wandering objects. Maybe life's precursors are cosmic travelers, hitching rides on chunks of ice and rock that drift between the stars. It's a beautiful idea, and it's testable. If panspermia is real, if comets really can deliver life's ingredients across interstellar space, then we'd expect interstellar comets to carry specific types of molecules. Water, obviously, organic compounds, complex carbon chemistry, maybe even amino acids or other prebiotic molecules. When Borisov came through, scientists detected carbon monoxide, which told us that interstellar comets can carry carbon-based molecules. That was significant. It meant the chemistry necessary for life can survive the journey through interstellar space. 3I divided by Atlas takes this further. It has massive amounts of water. Not just trace amounts, but enough water that it's expelling 40 kilograms per second and still has plenty left. This thing is basically a water tanker from another star system. And water is essential for life as we know it. Every living thing on Earth, from the simplest bacteria to the most complex organisms, requires water. Our biochemistry is built around it. Our cells are mostly water. Our DNA only works in aqueous solution. If panspermia delivered water to young planets billions of years ago, 3I divided by Atlas is proof that the mechanism exists. That objects like this really can transport enormous quantities of water across the galaxy. But here's where it gets interesting. 3I divided by Atlas has water, but it's depleted in many of the complex organics we'd expect if it were a perfect panspermia delivery system. It has the solvent, the medium for life, but not all the ingredients. What does that mean? One possibility is that panspermia isn't a single delivery. Maybe it's a multi-stage process. Maybe some comets bring water, others bring organics. Maybe the full suite of life's ingredients arrives piecemeal, and only worlds that receive the right combination, in the right sequence, in the right conditions, end up developing life. That would make life much rarer than if every comet carried everything. But it would still mean that life's building blocks are distributed throughout the galaxy, waiting for the right circumstances to come together. Another possibility is that 3I divided by Atlas's particular chemistry tells us something about its origin system. Maybe it formed around a star with different elemental abundances. Maybe its home system was poor in certain elements, which led to comets with unusual compositions. If that's true, then studying 3I divided by Atlas is like doing stellar archaeology. We're learning about the chemistry of a star system we can't directly observe billions of light years away by analyzing the comet it produced. There's also a darker possibility that some researchers have mentioned, though usually not in formal papers. What if the depletion of organics isn't natural? What if something processed this object? I'm not talking about aliens necessarily. I'm talking about the harsh conditions of interstellar space. 10 billion years is a long time. Cosmic radiation is relentless. High-energy particles slam into molecules, breaking bonds, altering chemistry. Maybe 3I divided by Atlas started out rich in organics, but the journey destroyed them. Maybe by the time an interstellar comet arrives at a new star system, most of the complex chemistry has been degraded, leaving only the most stable compounds. If that's the case, it has profound implications for panspermia. It might mean that only very specific molecules, ones that can survive eons of radiation, make the journey, and that the chemistry that arrives isn't the chemistry that departed. But there's still another angle here, one that connects back to the artificial hypothesis in an unexpected way. If you were designing a probe to study other star systems, what would you make it out of? You'd want something that could survive millions or billions of years in space. Something that could withstand radiation, temperature extremes, micrometeorite impacts. You might encase it in ice. Thick, protective ice that ablates away slowly, shielding the interior from radiation. Ice that also serves as propellant for minor course corrections, using sublimation as a form of thrust. And if you were really smart, you'd make the ice carry information. You'd encode data in the molecular composition, in the ratios of isotopes, in the specific arrangement of compounds. The ice wouldn't just be protection and fuel. It would be a message. I'm not saying that's what 3I divided by Atlas is. I'm saying that if someone wanted to send a probe disguised as a natural object, this is exactly how you do it. You'd make it look like a comet. You'd give it chemistry that's just unusual enough to attract scientific attention, but not so bizarre that it's obviously artificial. You'd put it on a trajectory that brings it close to multiple worlds, giving it opportunities to observe and gather data. And you'd time its arrival for an era when the target civilization has developed the technology to study it, but not yet the capability to intercept it. Again, this is speculation. Wild speculation. But it's worth thinking about, because if we ever do encounter genuine artificial objects from other civilizations, they might not look like what we expect. They might not be sleek metallic spacecraft with visible technology. They might look like rocks, or comets, or asteroids. The perfect camouflage for a probe is to make it indistinguishable from natural objects until someone looks closely enough to notice the anomalies. And with 3I divided by Atlas, we're looking closely. Very closely. And the more we look, the more anomalies we find. What the spacecraft are seeing, let me tell you about what's happening right now, at this very moment, as 3I divided by Atlas continues its journey through our solar system. The Mars Perseverance rover, sitting on the surface of Mars in Jezero crater, pointed its cameras at the sky on October 3rd, 2025. The images it captured show a faint streak against the background stars. That streak is 3I divided by Atlas. This is the first time we've ever photographed an interstellar object from the surface of another planet. Think about that. We've sent a machine to Mars, and that machine is now observing a visitor from another star system. The perspective this gives us, the parallax measurements, the ability to coordinate observations from multiple worlds simultaneously, is unprecedented. The Mars Reconnaissance Orbiter, circling Mars from orbit, is using its spectrometers to analyze the comet's composition. It's measuring how the coma evolves as the comet moves. It's tracking the jets, watching for changes, looking for patterns. And it's finding things. Things that haven't been fully released to the public yet because the data is still being analyzed. But there are rumors coming out of the Mars science team. Whispers about unexpected spectral lines, talk of activity patterns that don't match the models. I don't have confirmation on any of this, but the fact that there are whispers at all is significant. Scientists don't usually whisper unless something is genuinely surprising. Meanwhile, at Jupiter, the Juno spacecraft is preparing for 3, divided by Atlas's closest approach in late October. Juno has instruments designed to study magnetic fields, radiation environments, and plasma interactions. When 3 divided by Atlas passes through Jupiter's magnetosphere, Juno will be watching. This is important because Jupiter's magnetic field is enormous. It's the largest structure in the solar system made by a single object. And when a comet passes through it, the interaction between the comet's own plasma environment and Jupiter's field can tell us incredible amounts about the comet's internal properties. If 3 divided by Atlas is just ice and rock, the interaction will look one way. If it has unusual electrical properties, if there's something about its internal structure that's different from normal comets, the interaction will look different. We should get that data within weeks. There's also been talk, unconfirmed but persistent, about a rapid response mission. The idea would be to launch a small spacecraft on a fast trajectory to intercept 3 divided by Atlas before it leaves the inner solar system. It wouldn't be a complex mission, just a flyby with cameras and spectrometers, but it would give us close-up data that we can't get from Earth-based or existing spacecraft observations. The problem is timing. Launching a mission takes months of planning and preparation. By the time a spacecraft could be built and launched, 3 divided by Atlas might already be too far away. You'd need something that's almost ready to go, something that could be repurposed quickly. There are rumors that certain agencies are looking at exactly this possibility, that there are contingency plans being discussed, that if the data from Mars and Jupiter shows something truly extraordinary, there might be an attempt to get closer. I don't know if that's true, but I know that if I were in charge of a space agency and if I had the capability, I'd be seriously considering it. Because here's the thing, interstellar objects are rare. We might not get another chance like this for decades. Oumuamua came and went before we fully understood what we were looking at. By the time scientists realized how strange it was already too far away to study properly. We're not making that mistake with 3 divided by Atlas. We're watching it closely from the moment of discovery. We're throwing every available resource at it. We're coordinating observations across multiple wavelengths from multiple locations with multiple instruments. And what we're learning is that this object is even stranger than we initially thought. One detail that's emerged recently involves the comet's rotation. Most comets rotate, spinning as they travel, and the rotation period can tell you about the object's shape and mass distribution. Early observations of 3 divided by Atlas suggested a rotation period of about 8 hours. That's not unusual. Many comets spin at roughly that rate. But as astronomers collected more data, they noticed something odd. The rotation period isn't constant. It's changing. Very slightly, but measurably. Comets can change their rotation rates because of outgassing. When jets fire off from the surface, they exert torque, which can speed up or slow down the spin. This is a known phenomenon. But the rotation changes in 3 divided by Atlas don't correlate with the observed jet activity in the way you'd expect. The timing is off, the magnitude is wrong. It's like something is affecting the spin that we can't see directly. One explanation is that there are jets firing from regions we can't observe, maybe on the far side of the nucleus that's never pointed toward Earth. That's possible. Another explanation is that the internal structure is more complex than we assumed. Maybe mass is shifting inside the comet as different ices sublimate at different rates. Maybe the interior is layered in unusual ways, And as material is lost from the surface, the mass distribution changes, which affects the rotation. Or maybe something else is going on. Something that requires us to think differently about what this object is. The Centaur connection. There's a class of objects in our solar system called centaurs. They're icy bodies that orbit in the region between Jupiter and Neptune. And they're weird. They have characteristics of both comets and asteroids. They're not quite one thing or the other. Centaurs are thought to be objects that were ejected from the Kuiper belt, that distant region beyond Neptune, and got scattered inward by gravitational interactions. They're pristine, barely processed by solar radiation, and they contain some of the most ancient ice in the solar system. When scientists study the optical properties of centaurs, they find that deep negative polarization signature, that unusual red color. Those characteristics that suggest formation in extremely cold, distant environments. 3I divided by Atlas has the optical signature of a centaur. But it's not from our solar system, it came from outside. So either it formed in conditions similar to what created our centaurs, which would be a remarkable coincidence, or centaur-like objects are common throughout the galaxy. If the latter is true, it tells us something profound about planetary system formation. It suggests that the process that creates these icy bodies in the outer reaches of star systems is universal, that every system with giant planets probably has a population of scattered icy objects in distant orbits, slowly leaking into interstellar space. And if that's the case, then interstellar space is full of these things. Absolutely full. We've only detected 3 interstellar visitors, but that's because they're hard to spot. They're small, they're dark, and they move fast. There could be dozens passing through our solar system at any given time. Hundreds, maybe thousands. We just can't see most of them. This has implications for everything from solar system formation to the frequency of panspermia to the probability that Earth has been hit by interstellar objects in the past. Think about it. If comets from other star systems regularly pass through our solar system, some of them must have hit Earth. Over 4.5 billion years, the odds are overwhelming that our planet has been struck by at least a few interstellar impactors. Did those impacts deliver water? Did they bring organic compounds? Did they fundamentally alter Earth's chemistry at critical moments in our planet's history? We don't know. But 3I divided by Atlas is giving us the tools to start answering those questions. Because every measurement we make, every spectrum we capture, every data point we collect about this comet is information about what interstellar chemistry looks like. And that information lets us build models of what past interstellar impacts might have delivered. If 3I divided by Atlas represents a typical interstellar comet, then we now know that such objects can carry enormous amounts of water, moderate amounts of carbon dioxide, and lower levels of complex organics. If that's what hit early Earth during the heavy bombardment period billions of years ago, it would have contributed to our oceans. It would have altered our atmosphere. It would have provided raw materials for the chemistry that eventually led to life. In that sense, 3I divided by Atlas isn't just teaching us about itself. It's teaching us about our own history, about where we came from, about the cosmic processes that made Earth habitable. That's the real significance of this object, regardless of whether it's natural or artificial, regardless of whether all the anomalies have mundane explanations or hint at something more exotic. 3I divided by Atlas is a messenger, and the message it's delivering is about the nature of matter and chemistry and water distribution throughout our galaxy. The physics of impossible things. Let's talk about something that doesn't get mentioned much in the popular coverage of 3I divided by Atlas, but that has physicists scratching their heads. The object's trajectory and speed when you analyze them carefully, present a puzzle. 3. I divided by Atlas is moving at about 130,000 miles per hour relative to our sun day. That's fast, but it's actually on the slow end for interstellar objects. Oumuamua was moving faster. Borisov was moving faster. The speed an interstellar object has when it enters our solar system tells you something about its origin. Specifically, it tells you about its velocity relative to the local standard of rest, which is basically the average motion of stars in our galactic neighborhood. Objects that formed locally, that were ejected from nearby star systems relatively recently, tend to have higher velocities. They're still moving fast from the gravitational kick that sent them into interstellar space. Objects that have been wandering the galaxy for a long time, that have had billions of years to exchange momentum with passing stars and molecular clouds, tend to move slower. They've been gravitationally relaxed. 3. I divided by Atlas's relatively slow speed suggests it's been traveling for a very long time, which matches the age estimates. But here's the weird part. If you've been traveling through the galaxy for 10 billion years, you should have encountered a lot of gravitational perturbations. Every time you pass near a star, your trajectory bends a little. Every time you drift through a molecular cloud, drag forces act on you. Over billions of years, these effects accumulate. The trajectory should be randomized. Your direction of travel should have no relationship to where you started, because you've been scattered so many times. And yet, when astronomers trace 3, I divided by Atlas's path backward, when they calculate where it came from, they can identify a region of the galaxy that's consistent with the thick disk, the ancient stellar population they think the comet originated from. How is it possible for an object to travel for 10 billion years and still have a trajectory that points back to its birthplace? The answer is that it's probably not pointing directly back. Space is big, and the margin of error on these calculations is huge. We can identify a general region, but not a specific location. But still, the fact that we can identify any correlation at all is surprising. You'd expect the path to be completely scrambled by now, unless it hasn't been wandering randomly, unless its journey was more direct than we assume. What if 3I divided by Atlas was ejected from its home system with enough velocity that it effectively escaped the gravitational influence of the galaxy's core? What if it spent most of the last 10 billion years traveling through relatively empty space, far from stars, far from molecular clouds, with very few gravitational interactions? That could work. That would preserve the directionality of its initial trajectory. But it would require a hell of an ejection velocity. You'd need something catastrophic to kick an object that hard. A supernova? Maybe. Or a close encounter with a black hole? Or a stellar collision. Something violent enough to accelerate a 20-kilometer object to speeds well above the escape velocity of the galaxy's gravitational potential. Those events happen. They're rare, but over the lifetime of the galaxy, they occur. And if 3I divided by Atlas was born in such an event, it would explain both its ancient age and its preserved trajectory. But there's another possibility, one that requires us to think about propulsion. If an object has even a very small amount of thrust, if it can make minor course corrections over time, it could maintain a specific trajectory across vast distances. The thrust wouldn't have to be continuous, just occasional nudges to counter gravitational perturbations and keep the path on target. For a natural comet, there's no mechanism for this. Outgassing is random, driven by solar heating, and it doesn't provide directional control over billions of years. But for an artificial object, it's trivial. You'd build in a navigation system, a way to monitor your trajectory and make corrections. You'd use outgassing as propulsion, venting material in specific directions to generate thrust, and from the outside, it would look exactly like a normal comet. jets of gas and dust. Activity that correlates roughly with solar distance. Nothing obviously technological, until you look closely at the details, at the specific directions of the jets, at the timing of the activity, at the relationship between thrust and trajectory changes. That data is being collected right now, and within months, we'll know if the trajectory of 3I divided by Atlas can be fully explained by gravity and random outgassing, or if there's something else affecting its path. The silence problem. Here's a question that doesn't get asked enough in discussions about potential artificial interstellar objects. If 3I divided by Atlas is a probe, if it really is some kind of technology from another civilization, why isn't it doing anything obvious? If I wanted to study another star system, if I sent a probe on a billion-year journey to collect data, I'd make damn sure that probe was capable of communication. I'd give it a transmitter. I'd have it send signals, either back to wherever it came from or broadly into space so that any technological civilization in the area could detect it. 3I divided by Atlas isn't transmitting. At least, not anything we can detect. Radio telescopes have been pointed at it. Multiple facilities across multiple frequencies listening for any sign of artificial signals. Nothing. No radio emissions beyond what you'd expect from natural plasma interactions in the coma. So either it's not artificial or it's staying quiet deliberately. Why would it stay quiet? One possibility is that it's passive. It's designed to observe, not to communicate. Maybe the beings who built it, if they exist, don't want to make contact. They just want data. They're watching, learning, studying, but not announcing their presence. That's a perfectly reasonable strategy if you're trying to study a civilization without influencing it. You don't want your presence to change the behavior of what you're observing. So you stay hidden. You look like a natural object. You collect your data and move on. Another possibility is that it's not transmitting now, but it will later. Maybe it's programmed to remain silent until certain conditions are met. Maybe it's waiting to see if we notice it. Maybe it's testing whether we're capable of recognizing anomalies, of asking the right questions, of taking it seriously. And if we pass that test, if we demonstrate sufficient scientific capability and curiosity, then maybe it reveals itself. Maybe it activates systems that have been dormant for billions of years. Maybe it starts communicating. That sounds like science fiction, but it's also a logical strategy if you're trying to make contact only with civilizations that have reached a certain level of technological and scientific maturity. There's also a darker possibility. Maybe it was transmitting, but we missed it. Maybe it sent signals decades ago before we were listening, or in frequencies we weren't monitoring, or using modulation schemes we couldn't recognize. Maybe the wow signal wasn't from a star. Maybe it was from this object, announcing its presence as it approached, and we only caught one brief snippet before it moved on to other forms of communication we can't detect. That's pure speculation. I have no evidence for it. But the timing is interesting. A signal in 1977, an object arriving in 2025, coming from the same direction. If it was traveling at the speeds we measure, it would have been at the edge of our solar system in the late 1970 seconds. Just close enough that a powerful transmission could reach Earth. Again, probably coincidence. But it's the kind of coincidence that makes you think. What we're really afraid of. Let me be honest about something that underlies a lot of the resistance to taking the artificial hypothesis seriously. It's not that scientists think the evidence is insufficient. I mean, they do think that, and they're probably right. But there's something deeper going on. It's fear. If 3I divided by Atlas is artificial, if it really is a probe from another civilization, then several things become true that are psychologically difficult to process. First, it means we're not alone. That's huge. That's species level significant. It changes everything about how we understand our place in the universe. Second, it means that civilization is ancient. 10 billion years. The object has been traveling for twice as long as Earth has existed. Whatever made it is either incredibly long-lived or it's gone, extinct, dead. And it left behind this messenger, this artifact, still functioning eons after its creators disappeared. That's terrifying. The idea that civilizations can arise, develop technology, send probes across the galaxy, and then vanish, all while their creations continue traveling through space, outlasting them by billions of years. It makes you wonder about the fate of all technological species. Are we temporary? Are we just a brief flicker in cosmic time, destined to burn out while our own probes keep flying long after we're gone? Third, if the object is here, in our solar system, passing close to our planets, then it's observing us. Right now, it's watching, studying, taking notes on who we are and what we're doing. That's an uncomfortable feeling. The idea that we're being examined by an intelligence we can't communicate with, that's been watching the evolution of Earth for who knows how long, that might understand us better than we understand ourselves. These psychological barriers make it very hard for scientists to seriously engage with the artificial hypothesis, even when the evidence is suggestive. Because accepting the possibility means accepting these implications. And most people, scientists included, would rather explain away anomalies with complicated natural processes than confront the implications of contact, even passive contact, with another technological civilization. I get it. I understand the resistance. If I'm being honest with myself, I share it. Part of me wants 3I divided by Atlas to just be a weird comet, a natural object with unusual chemistry and strange physics, but ultimately just a product of cosmic processes we don't fully understand yet. That would be easier, cleaner, less philosophically disturbing, but wanting something doesn't make it true. And the data is the data. The next few months. So, where do we stand right now? What's the current state of our knowledge? And what can we expect in the coming weeks and months? Here's what we know for certain. 3I divided by Atlas is the third confirmed interstellar object. It's the largest, oldest, and most active such object ever detected. It has multiple anomalies that don't fit standard comet models. It's currently making close approaches to Mars and Jupiter, and multiple spacecraft are observing it intensively. Here's what we suspect, but aren't certain about. The object's age is around 10 billion years, making it a sample of ancient galactic chemistry. Its internal structure is unusual, possibly layered or porous in ways we haven't seen before. It has an energy source that allows water activity far from the sun, though the nature of that source is unclear. Here's what we don't know. Whether all the anomalies can be explained by exotic but natural processes, or whether some of them require fundamentally new physics or even artificial origins. What we'll find when we get better data from the Mars and Jupiter observations. Whether there are more surprises waiting as the object continues through the inner solar system. And here's what's going to happen next. Over the next few weeks, data from the Mars observations will be fully analyzed and published. We'll get spectroscopic information at wavelengths we've never accessed before. We'll see how the comet's activity responds to its changing distance from the Sun. In late October, the Jupiter encounter will occur. Juno will collect data on how 3I divided by Atlas interacts with Jupiter's magnetosphere, which will tell us about the comet's internal structure and composition. By December, we should have a comprehensive data set from multiple sources. Enough information to start answering some of the fundamental questions about what this object really is. And then, depending on what we find, decisions will be made about follow-up observations. Maybe there will be a mission proposal to intercept the comet before it leaves. Maybe there will be campaigns to observe it from the outer solar system as it departs. Or maybe the data will be so extraordinary that it forces a broader conversation about what we're looking at and what it means. I don't know what we're gonna find. Nobody does. That's what makes this exciting. That's what makes this one of the most important astronomical observations happening right now. For the first time in human history, we're studying an interstellar visitor with the tools and technology to really understand it. We're not letting it slip away while we argue about what it might be. We're gathering data, we're running analyses, we're following the evidence wherever it leads. And within a few months, we'll have answers. Maybe not complete answers. Maybe not final answers. But real information that will either confirm this is just a strange but natural object, or that will deepen the mystery in ways we can't yet predict. The broader implications. Let me zoom out for a minute and talk about what all of this means. Regardless of whether 3I divided by Atlas turns out to be natural or something else, we're living through a revolution in how we understand the universe and our place in it. 15 years ago, we didn't even know if planets existed around other stars. Now we've detected thousands of exoplanets. We know that planetary systems are common, that many stars have worlds orbiting them. 10 years ago, we had never detected an interstellar object. Now we've found 3. We're learning that space isn't empty, that there's traffic between the stars, that material, chemistry, maybe even life, travels across the galaxy. 5 years ago, the idea of seriously searching for signs of technological civilizations was fringe science. Now SETI has mainstream funding. Universities have astrobiology programs. NASA is investing in technosignature research. We're in the middle of a paradigm shift. And 3I divided by Atlas is happening right at this pivot point. Right when we're transitioning from thinking of ourselves as isolated on one planet, around one star, to understanding that we're part of a galactic ecosystem where matter and energy and information flow between systems. If 3I divided by Atlas is natural, it's still profound. It's still teaching us that our models of cometary chemistry need revision, that interstellar objects carry ancient information about conditions in the early galaxy, that the universe is stranger and more diverse than we imagined. If it's artificial, that's obviously even more significant. It means we're not alone. It means technology is possible on scales we've barely imagined. It means our future might include contact, communication, understanding of other minds that arose under different stars. Either way, this matters. This is important. This is the kind of discovery that changes not just science, but philosophy, culture, how we think about ourselves as a species. And we're watching it happen in real time, the unanswered questions. Let me list out the major questions that remain unanswered, the things we genuinely don't understand yet about 3I divided by Atlas. What is the nature of its internal energy source? How is it sublimating water at distances where solar heating alone can't account for the activity? Is there radioactive decay? Tidal heating from internal stresses? Something else entirely? Why is the nickel-iron ratio so anomalous? Is this really natural chemistry from an exotic formation environment? Or is it evidence of processing we can't explain? What controls the jet directions? Why do some jets point toward the sun when they should be pointing away? What mechanism is powerful enough to overcome solar wind pressure? How has this object preserved its pristine optical properties for 10 billion years? Why hasn't cosmic radiation degraded it the way we'd expect? Is the trajectory correlation with multiple planets really just coincidence? Are the probabilities telling us something important, or are we falling into the trap of seeing patterns in randomness? What's the connection, if any, between this object and the WOW signal? Is it meaningful that they come from the same region of the galaxy, or is that purely chance? These are the questions that observations over the next few months might help answer, or they might just raise new questions. That's how science works. Every answer leads to more questions. The Rosetta Stone. There's a reason scientists keep calling 3I divided by Atlas a Rosetta Stone. The original Rosetta Stone was a key that unlocked Egyptian hieroglyphics that let us read and understand a dead civilization's written language. 3I divided by Atlas might be the key that unlocks our understanding of how planetary systems form across the galaxy, how chemistry evolves in different environments, how water and organic compounds travel between stars, how the early universe built the raw materials that eventually became planets, moons, and maybe life itself. Every measurement we make of this comet is a data point about conditions billions of years ago, billions of light years away. Every spectrum is a glimpse into chemistry we can't reproduce in laboratories. Every trajectory calculation is information about gravitational dynamics on scales we rarely get to study directly. Even if every single anomaly turns out to have a natural explanation, even if the nickel ratio is just exotic formation chemistry, even if the water activity is just unusual internal structure, even if the trajectory is just cosmic coincidence, we're still learning things we could never learn any other way. Because you can't go to another star system and collect samples. Not with current technology. Not for decades, maybe centuries. The only way we get to study material from other stellar systems is when that material comes to us. And right now, 20 kilometers of ancient ice and rock from the early Milky Way is flying through our cosmic backyard, close enough to study in detail. That's unprecedented. That's the opportunity of a generation. And the scientific community knows it. That's why there's so much excitement. That's why multiple spacecraft are being redirected to observe it. That's why researchers are scrambling to analyze every piece of data as quickly as they can. Because this won't last. 3I divided by Atlas is moving at 130,000 miles per hour. It's going to make its closest approaches to the inner solar system planets, swing around the sun, and then head back out into interstellar space. Within a couple of years, it'll be too far away to study effectively. And we might not get another chance like this for a very long time. Oumuamua caught us by surprise. We didn't have time to organize proper observations. By the time we understood what we were looking at, it was already leaving. Borisov gave us more time, but it was smaller, dimmer, harder to study in detail. 3I divided by Atlas is big, bright, active, and we spotted it early enough to plan comprehensive observations. This is the first time we're really ready to study an interstellar visitor properly. And what we're finding is that we were not prepared for how strange it would be. The hypothesis pyramid. Let me walk you through how scientists think about this problem, because there's a hierarchy of explanations that gets considered before you ever get to artificial origins. At the base of the pyramid, the first layer of explanation, you have standard physics and chemistry. Can we explain the observations using well-understood processes? For most astronomical objects, the answer is yes. You apply known physics, you get predictions that match observations, and you're done. For 3I divided by Atlas, this doesn't work. Standard comet models don't predict the water activity we're seeing. Normal chemical fractionation doesn't produce nickel without iron. Regular outgassing doesn't create anti-tails. So, you move to the second layer. Exotic, natural processes. Maybe there are physical or chemical phenomena we don't fully understand, but that are still fundamentally natural. Unusual molecular chemistry, rare structural configurations, low probability events that happen occasionally but that we haven't studied much because they're uncommon. This is where most scientists are focusing their efforts with 3I divided by Atlas. They're trying to find exotic but natural explanations that can account for what we're seeing, and they're having some success. You can construct scenarios involving organometallic compounds and internal heating and layered structures that might explain individual anomalies. But here's the problem. Each anomaly requires its own specialized explanation. And when you start stacking multiple low probability explanations on top of each other, the combined probability starts getting very small. It's like saying, well, this could be explained if the comet formed in a very unusual environment, and it has a rare internal structure, and it happened to get ejected with an unusual trajectory, and it contains exotic molecules we've never detected before, and at some point, the combination of unlikely explanations becomes less probable than considering alternatives. Which brings you to the third layer. Unknown natural phenomena. Maybe there are physical processes we simply haven't discovered yet. New physics, new chemistry. Things that are completely natural but that we don't have in our textbooks because we've never observed them before. This is possible. Science has a long history of discovering new phenomena when we make observations that don't fit existing models. That's how we found dark matter, dark energy, quantum mechanics, relativity. We saw things that didn't make sense, and we realized the universe had rules we didn't know about yet. Could 3I divided by Atlas be showing us new physics? Maybe. But usually when you discover new physics, it's because the anomaly is stark and undeniable, and you have no choice but to accept that something fundamental is missing from your models. With 3I divided by Atlas, the anomalies are significant, but not quite that extreme. They're more like, this is really weird and we don't have great explanations, rather than, this is completely impossible under known physics. And that brings us to the fourth layer, the top of the pyramid. Non-natural origins. This is the explanation of last resort. You only go here when you've genuinely exhausted all other possibilities. When the data is so incompatible with natural explanations that you have no choice but to consider whether something else is going on. Most scientists don't think we're at that point with 3I divided by Atlas. They think we're still in layer 2 or 3, still working on exotic natural explanations or potentially unknown physics. But Avi Loeb and a few others are arguing that we should at least keep the fourth layer in mind as we collect more data. Not jump to it prematurely, but not dismiss it out of hand either. Because if we're too committed to natural explanations, if we're psychologically unable to seriously consider alternatives, we might miss something important. We might overlook signals in the data that could tell us we're looking at technology. That's the tension between being appropriately skeptical and being open-minded enough to recognize something truly extraordinary if it's actually there. The detection problem. Here's something that doesn't get talked about much. If there are artificial interstellar objects out there, objects created by other technological civilizations, how would we recognize them? We're used to thinking about SETI in terms of radio signals or optical flashes. We listen for transmissions. We look for intentional beacons. We search for evidence of communication. But that's not the only way technology manifests. If a civilization wanted to explore the galaxy, if they wanted to study other star systems, they might send physical probes. And those probes would need to be designed to survive incredibly long journeys through harsh environments. The best design might be to make them look natural, to camouflage them as asteroids or comets. to give them the appearance of ordinary objects so they don't attract attention from potentially hostile civilizations, or so they can study their targets without interference. If you were designing such a probe, you'd want a protective outer layer of ice and rock to shield against radiation. That's exactly what a comet looks like. A way to make minor course corrections without obvious propulsion systems. Outgassing from sublimating ice would work perfectly. The ability to survive for billions of years. You'd need to be big, massive enough that you don't erode away quickly. A way to gather data about any system you pass through. Passive sensors, maybe cameras and spectrometers built into the structure. And you'd want to look as natural as possible, unless and until you decide to reveal yourself. Now, I'm not saying that's what 3i divided by Atlas is, but I am saying that if artificial probes exist, this is what they might look like. And if that's true, then we have a detection problem. Because we don't have good criteria for distinguishing between a natural object with unusual properties and an artificial object designed to appear natural. That's the challenge. That's why this is so difficult. Every anomaly could be natural. Every strange observation could have a mundane explanation we just haven't thought of yet. And even if we had a genuine artificial object, we might rationalize away its unusual features because we're predisposed to expect natural explanations. The only way to be sure would be to detect something unambiguously technological, a radio transmission, a visible structure, evidence of manufacturing or deliberate design. And we haven't detected any of that with 3i divided by Atlas. So we're left in this uncomfortable middle ground. Looking at an object that's strange enough to raise questions, but not strange enough to force answers. The ethical dimension. Let me raise something that almost nobody is discussing publicly, but that matters if there's even a small chance. 3i divided by Atlas is artificial. If this is a probe, if it's observing us, what does that mean for how we should behave? Are we being tested? Are we being evaluated? Is our response to this object itself part of the observation? Think about it from the perspective of whoever might have sent this thing, if anyone did. You've launched a probe on a multi-billion-year journey to study other star systems. That probe has reached a system with a potentially technological civilization. What do you want to learn? You probably want to know if they're scientifically capable. Can they detect the probe? Can they study it? Can they recognize anomalies? Do they have the intellectual curiosity and scientific rigor to investigate properly? You might want to know if they're peaceful or aggressive. If they detect something unusual, do they try to destroy it or do they study it? Do they cooperate internationally to share data or do they keep secrets? You might want to know about their values. What do they care about? How do they react to the unknown? Are they driven by curiosity, by fear, by greed? All of that would be observable just by watching how we respond to the comet's presence. Now, this is wildly speculative. This assumes not just that the object is artificial, which is already a huge assumption, but that whoever made it cares about our response, which is another layer of assumption. But if there's even a tiny chance this is the case, it raises questions about how we should conduct ourselves. Should we be trying to communicate with it? Should we be respectful of it as potentially someone else's property? Should we be transparent about our observations and findings, or strategic about what we reveal? These are questions that humanity as a whole has never had to seriously consider before. We've never been in a situation where our actions might be observed and judged by another intelligence. And even if 3i divided by Atlas is natural, even if all of this is just academic speculation, these are questions we're going to have to answer eventually, because we're going to encounter more interstellar objects. We're getting better at detecting them. Our technology is improving, And sooner or later, we might find one where the evidence of artificial origins is undeniable. What do we do then? The silence of the scientific community. Here's something I find interesting. If you read the formal scientific papers about 3I divided by Atlas, if you look at what researchers are publishing in peer-reviewed journals, you'll see detailed analyses of composition, trajectory, activity levels, all very technical and careful. What you won't see is much discussion of the artificial hypothesis. It's mentioned occasionally, usually in the last paragraph, often in the form of, while some have suggested non-natural origins, we consider this unlikely and focus our analysis on natural processes. But if you talk to astronomers privately, if you catch them in conversations at conferences or in late-night discussions, you'll hear something different. You'll hear fascination. You'll hear uncertainty. You'll hear people admitting that they don't have good explanations for what they're seeing. The public scientific discourse and the private scientific discourse are not the same. Why is that? Part of it is professional caution. Scientists are trained to be conservative, to avoid making claims they can't fully support, to stick with what they can prove. And that's good. That's how science should work. But part of it is also social pressure. The scientific community has a culture, and that culture looks down on people who take alien artifact hypotheses seriously. It's seen as sensationalist, as attention-seeking, as not rigorous. Avi Loeb has experienced this firsthand. He's a respected scientist with an impressive track record, but since he started arguing that we should seriously consider artificial origins for Oumuamua, and now 3I divided by Atlas, he's faced criticism from colleagues. Not scientific criticism of his analysis, but social criticism of his willingness to discuss the topic at all. That's a problem. Because if there's social pressure against considering certain hypotheses, even when the data is suggestive, then science isn't following the evidence wherever it leads. It's following the evidence only to places that are socially acceptable. I'm not saying scientists should start calling every weird observation aliens. That would be bad science. But I am saying that the artificial hypothesis should be on the table, should be evaluated on its merits against the data, without social stigma. And right now, it's not. Right now, even mentioning the possibility in a paper is risky for your reputation. That needs to change, because we're entering an era where we're going to detect more and more interstellar objects. We're going to find things that challenge our models. And if we're not psychologically and socially prepared to consider all possibilities, we might miss something critically important. The Fermi paradox connection. There's a famous question in astronomy called the Fermi paradox. If technological civilizations are common in the galaxy, if they develop the ability to explore and colonize, if they've had billions of years to spread, then where is everyone? Why haven't we seen evidence of alien civilizations? Why does the galaxy appear empty? 3I divided by Atlas connects to this question in interesting ways. If the object is natural, it tells us that interstellar space has traffic. Material moves between systems. Chemistry and water and maybe even organic compounds travel across the galaxy. That's relevant to understanding how life might arise and spread. But it also tells us that detecting and studying interstellar objects is hard. We've only confirmed 3. There are probably thousands passing through our solar system that we can't see. They're small, dark, fast-moving. They're easy to miss. If technological civilizations sent probes, lots of them, scattered throughout the galaxy to observe and study, we might not notice. We might be surrounded by artificial objects that look like natural comets and asteroids, and we'd never know. That's one solution to the Fermi paradox. They're here, but we can't tell them apart from natural objects. Another solution, if 3i divided by Atlas is artificial, is that it's a relic, that the civilization that made it is long gone. 10 billion years is a long time. Maybe they thrived for a while, sent out probes to explore, and then went extinct. And their technology outlasted them, continuing its mission long after its creators disappeared. That's a sobering thought. It suggests that technological civilizations might be common, but short-lived. That we all eventually fail, go extinct, and leave behind only artifacts that drift through space forever. Or maybe there's a different explanation. Maybe civilizations that survive long-term adopt a policy of quiet observation. They don't announce themselves. They don't make contact with younger species. They watch, they study, they collect data, but they don't interfere. If that's the case, if the galaxy is full of watchers who stay hidden, then we'd see exactly what we see. Occasional anomalies, strange objects that might be natural or might not be, signals that could be explained either way. Never quite enough evidence to be certain, but always enough to wonder. 3i divided by Atlas fits perfectly into that scenario. It's anomalous enough to attract attention if you look closely, but ambiguous enough that most scientists can rationalize it as natural. The perfect level of subtlety for something that wants to be studied by those capable of studying it, but not so obvious that it forces contact. I don't know if any of this is true, but these are the kinds of questions that objects like 3i divided by Atlas force us to think about. Questions about our place in the universe, about whether we're alone, about what it would mean if we're not. The technological readiness question. Let me ask you something. If tomorrow we got definitive proof that 3i divided by Atlas is artificial, what would we do? Would we try to intercept it? Would we attempt communication? Would we organize a crash program to launch a mission to study it up close before it leaves the solar system? The honest answer is, we probably couldn't. We don't have a spacecraft ready to launch on short notice. Building and launching an interstellar intercept mission takes years of planning and preparation. By the time we could get something ready, 3i divided by Atlas would be long gone. We could try to communicate, I suppose. Point radio telescopes at it, broadcast messages, see if anything responds. But we don't know what frequency to use, what modulation scheme, what language. And if it is a probe, it might not be designed to communicate with the civilizations it's studying. So we'd be left doing what we're doing now, observing from a distance, collecting data, analyzing, trying to understand, and that's fine. That's probably the right approach anyway. But it highlights how unprepared we are as a civilization for contact, even passive contact with an artifact, rather than direct communication with another intelligence. We don't have protocols, we don't have international agreements on how to respond, we don't have the technology to do much beyond observe. This is something humanity needs to think about, because interstellar objects are going to keep coming. We're going to keep detecting them, and eventually, we might find one where the evidence of artificial origins is undeniable. What do we do then? We need to have the conversation now before it becomes urgent. We need to develop capabilities, agreements, plans, not because we're certain we'll need them, but because if we do need them and don't have them, we'll have missed an opportunity that might never come again. The data deluge. Over the next few weeks, as the Mars and Jupiter observations are completed and analyzed, we're going to be flooded with data. Spectroscopic measurements across dozens of wavelengths, high-resolution images showing surface features and jet structures, magnetic field measurements, plasma environment readings, trajectory calculations with unprecedented precision. All of that data will be published, made available to researchers worldwide, analyzed by hundreds of scientists using different techniques, different models, different assumptions. And from that analysis, we'll start to get answers. Maybe we'll find that the nickel signature has a natural explanation after all, that there's a type of organometallic chemistry we didn't know about, but that makes sense once you understand it. Maybe we'll discover that the water activity is driven by internal heating from radioactive decay, and we can model it precisely once we know the composition. Maybe the anti-tail will turn out to be an optical illusion, a viewing angle effect, something that looks anomalous but is actually mundane. Maybe every anomaly will fall away as we get better data, and 3I divided by Atlas will become just an unusually interesting natural comet. Strange, yes, but ultimately explicable within the framework of known physics and chemistry. That's the most likely outcome, honestly. Most scientific mysteries turn out to have mundane solutions once you gather enough data. But maybe not. Maybe we'll find new anomalies. Maybe the high-quality data from close-up observations will reveal things that are even harder to explain. Maybe the mystery will deepen. And if that happens, if the evidence continues to accumulate that there's something genuinely different about this object, then the conversation will change. Right now, the artificial hypothesis is fringe. It's what a few bold scientists are willing to discuss publicly, and what many more discuss privately but won't put in papers. But if the data supports it, if natural explanations continue to fail, that will shift. The hypothesis will move from fringe to legitimate. More researchers will take it seriously. More resources will be devoted to testing it. And at that point, we'll be in truly unprecedented territory. Not just scientifically, but culturally, philosophically, existentially. The perspective shift. Let me tell you what I think is the real significance of 3I divided by Atlas, regardless of what it turns out to be. It's forcing us to confront the reality that we're not isolated, that our solar system is not a sealed bubble floating in empty space, that we're part of a larger environment, a galactic ecosystem where things move between systems, where chemistry and material and information flow. For most of human history, we thought Earth was the center of everything. Then we realized we orbit the Sunday. Then we realized the sun is one star among billions. Then we realized the Milky Way is one galaxy among trillions. But even as our cosmic address kept expanding, we still thought of ourselves as somehow separate. Our solar system, our neighborhood, our space. Interstellar objects are breaking down that illusion. They're showing us that space is not empty, that there's traffic, that what happens in other stellar systems affects us, that we're downstream from cosmic processes happening all across the galaxy. 3I divided by Atlas is a physical object from another part of the galaxy, carrying chemistry from 10 billion years ago, passing through our space within reach of our instruments. That's profound. That changes how we think about our place in the cosmos. And if it turns out to be artificial, that changes things even more dramatically. It means we're not just part of a chemical ecosystem. We're part of a potentially technological ecosystem. A community of minds, of civilizations, of intelligences that have arisen across the galaxy over billions of years. Even if we never communicate with whoever made it, even if they're long dead, the mere existence of the artifact tells us something fundamental about the universe. We're not alone in having reached for the stars. Others have done it before us, and they've left traces, evidence, monuments to their existence. That's the perspective shift. That's what 3I divided by Atlas represents. Whether it's a comet or a probe, it's a messenger. And the message is, you're part of something bigger. The choice ahead. Here's where we are. We have an object with multiple anomalies. We have hypotheses ranging from exotic natural processes to artificial origins. We have ongoing observations that will give us much better data within weeks. And we have a choice to make as a civilization. Do we approach this with closed minds, insisting that natural explanations must exist and refusing to seriously consider alternatives? Or do we approach it with open minds, following the evidence wherever it leads, even if that makes us uncomfortable? I'm not advocating for believing in aliens without evidence. I'm advocating for honest, rigorous science that doesn't dismiss possibilities prematurely. If 3I divided by Atlas is natural, great. We'll figure out the chemistry and physics, we'll publish papers, we'll learn something about the universe. That's a win. If it's artificial, or if it's something we don't understand yet that requires new physics, that's also great. That's a bigger win. That's discovery at the highest level. But if we're so committed to one explanation that we ignore evidence for alternatives, we might miss the discovery of a lifetime. That's the choice. And it's not just up to scientists, it's up to all of us. Because how we respond to this, how we think about it, how we talk about it, shapes the culture that scientists work in. It affects what's acceptable to discuss, what's considered serious, what gets funding and attention. If we mock the idea that 3I divided by Atlas might be artificial, if we dismiss it as crazy without looking at the evidence, we create an environment where scientists are afraid to explore unconventional ideas. But if we're thoughtful, if we say, let's look at the data, let's see what we can prove, let's be open to surprises, we create an environment where real discovery can happen. The final mystery. Let me end with this. Right now, tonight, as you're watching this, 3I divided by Atlas is out there. It's moving through space at 130,000 miles per hour. It's approaching Jupiter. Spacecraft are watching it. Instruments are recording data. And we still don't really know what it is. We know it's old. We know it's big. We know it does things comets aren't supposed to do. We know its chemistry is strange and its trajectory is remarkable. But we don't know if it's a natural wonder or something more. And that's okay. That's how science works. You don't get instant answers. You gather data, you analyze, you test hypotheses. Sometimes for years, sometimes for decades. But here's what's certain. 3I divided by Atlas is teaching us. It's showing us that the universe is stranger than we thought, that interstellar space is more active than we imagined, that chemistry and physics in other parts of the galaxy can be fundamentally different from what we see locally. It's expanding our understanding of what's possible, and that's valuable regardless of what the object turns out to be. In the coming months, we'll learn more. We'll get better data. We'll refine our models. We'll either solve the mysteries or discover new ones. And through all of it, we'll be doing what humans do best, looking at the unknown and trying to understand it, asking questions, seeking answers, refusing to accept ignorance when knowledge is within reach. That's the real story of 3I divided by Atlas. Not whether it's natural or artificial, but that we noticed it, that we're studying it, that we care enough to devote resources and time and intellectual energy to figuring out what this visitor from another part of the galaxy really is. Whatever we discover, the journey is worth it. Because every time we look closely at something strange, every time we refuse to dismiss anomalies, every time we follow the evidence even when it makes us uncomfortable, we get closer to understanding the universe we live in. And understanding the universe means understanding ourselves, our origins, our context, our place in the cosmic story. 3 I divided by Atlas is a chapter in that story. Maybe a footnote, maybe a major turning point. We'll find out soon enough. But either way, it's a reminder that we live in a universe full of wonders, full of mysteries, full of things we don't understand yet, but might someday. And that's what makes it all worthwhile. The comet from 10 billion years ago, carrying chemistry from the ancient galaxy, passing through our solar system at this exact moment in history when we have the technology to study it properly, is telling us something. The universe is vast and strange and full of surprises, and we're just beginning to understand it. Subscribe for the analysis of the Jupiter encounter data when it drops.